In this video, we are going to discuss one point that's very important regarding Bernoulli equation. And to discuss this point, we need to quickly revise some things that we discussed before we do the derivation of Bernoulli equation, which is the assumptions that we made to make this derivation for Bernoulli equation. So among the assumptions is that the flow is inviscid, meaning that there is no viscous losses, and there is no pumps or turbines that will change the energy of the fluid. And when we look at the equation and see the applicability of this equation, we would see that it's very, very limited, because we have a lot of cases where there is a pump or a turbine. The losses that we assume that there are no losses. This is something that we cannot avoid. Any flow, due to the viscosity of the fluid and the friction between the walls of the pipe and the fluid, will lead to some losses, and these losses cannot be avoided, as I just said. So the equation is very, very limited and is not practical for most of the cases. So that's why we use what we call the general energy equation, or what's sometimes called modified Bernoulli equation. It's called modified Bernoulli equation because, as we will see it now, the equation is almost the same as Bernoulli equation, with just few tweaks to the equation to make it more general. The derivation is available in the textbook in section 5.6, and you can go and check it if you're interested. But for the sake of time, and to make this point clear without going through a lot of derivations, I'm going to show the final form of the equation. So this is the final form of the equation, which looks similar to the original Bernoulli equation. So we'll see that these three terms here and these three terms here are the same terms we used to see in Bernoulli equation. There is one extra term here, and there are two extra terms here. So the as we said many times before, this equation is written in units of head, which is length, meter or foot or any equivalent unit. And we also said before that the Bernoulli equation can be written in units of head, or specific energy like joule per kilogram, or energy or power, joules per second or whatever. So just to know what these new terms mean, the H pump is the I think the name is clear. It has something to do with the pump. So this is the energy that the pump provides to the fluid. We call it H because it's useful head, and we will discuss what we mean by useful later. The H turbine is the energy lost or extracted. This is why we call it turbine E. The energy extracted from the fluid, or the head extracted from the fluid by a turbine. And HL is the irreversible head losses due to the components of the piping system. And these are the three terms that we added. So they represent the three types of things that we mentioned before: the energy added by a pump, etc., or removed by a turbine, or lost as mechanical losses. This last term here is going to be discussed in details in chapter 8, and we will spend the whole chapter 8 just to know how to calculate these losses by the knowledge of the shape of the pipe, the dimensions, the type of flow, and a lot of things. So this is something that we are going to discuss in a lot of details later. I'm going to keep it for later. For now, if we are going to solve some problems before we reach chapter 8, we will just say that the losses are given. We know the value of the losses, and we are just going to go through it. But for these two terms, the H pump and H turbine, I'd like to kind of see how we got these equations. So these equations for the pump and the turbine are not new equations. We already discussed them before, and we discussed them before even we do the derivation of Bernoulli equation, when we were discussing the types of energy that we are considering, And we said that the kinetic potential and flow work are the energies types that we are going to consider. And we said that we just focus on these three types of energy because these are what we call the mechanical energy, that the form of energy that can be converted into mechanical work using a pump or a turbine. So this is when we discussed these two terms before. So to quickly revise the equations, this is the first case of a turbine where there is mechanical work going in and the electric work coming out. This is the function of the turbine, and we said that the efficiency of the turbine is the outlet over the inlet, which is the electric work out over the mechanical work in, and both works are in terms of in units of joules per second. This is power. And as we did for all terms in Bernoulli equation, we can convert this or represent this in terms of head by dividing by mg. And this is what we call the turbine head. Okay, so this H turbine is the mechanical work in. This is the work in the turbine, which is lost or extracted from the fluid. So this is the same thing. The mechanical in, it's the in to the turbine or extracted from the fluid over mg, and the work mechanical in is the electric work out over the overall efficiency over mg. So if we go back to the previous slide, this is the turbine, work turbine, which is the electric work produced by the turbine over the efficiency of the turbine, which we call the overall efficiency. So it's the same thing over mg. Same thing for a pump. Pump is the same as a turbine, but as I hope it's clear here, this is electric work going in and mechanical work going out. So we're going to do the same thing. The efficiency is the out over the in, which is mechanical work out over the electric work in, and both have the units of power, which is joule per second. So if we divide the mechanical work out by the mg, we can get the H pump, which is the overall efficiency times the electric work in over mg, which is this. Okay, so this is not new. So we can understand how we got these two terms for the pump and the turbine. So now we can look at this diagram, because it gives a very nice illustration of the modified equation. So this is the mechanical work or the mechanical energy of the fluid, which is the three types of energy: potential, kinetic, and flow work. And if there is pump work, then the pump work, this is the electric power that we are providing. The electric power part of it is lost as mechanical losses, and the rest is provided to the fluid. Okay, so this is the H pump usable. U is usable. This is what the fluid used. And then for the output, we have the mechanical work of the mechanical energy of the fluid leaving the control volume, and then the mechanical losses, which is HL, and we have the extracted head by the turbine. This is all the extracted head. It's not what was converted into electricity. This is all the head. Part of it will be lost as in terms of losses, and part of it is converted into electricity. And it's very important here to understand these two terms, U, or these letters U and E, because we need to have a good understanding of this equation and what it is concerned with. This equation is concerned with the fluid. It's concerned with the fluid. Okay, so when we add the terms for the H pump, for the H losses and H turbine, we look at it from the fluid point of view. So when we look at the H pump, it's not how much electricity you provide, it's how much energy the fluid gained or used, gained from the pump. The same for the turbine. It's not how much electricity is produced, it's how much energy was lost from the fluid. So this has to be clear when we use this equation. There is a special case, which is we can consider as a special case. It's when we have the energy equation and we have يعني simple cases where there is an incompressible fluid where the densities are equal, so rho 1 equals rho 2. If there is no mechanical work, then H pump and H turbine are 0, and there is no losses, then H losses are 0. We go back to the original Bernoulli equation. So this is the modified Bernoulli equation. We are going to discuss some more details about the modified equation, and then apply it on some problems inshallah. So I'll see you next time inshallah. Goodbye.